All right, guys, so this is a two-part lecture on the electronic structure of atoms. In the first part, we're going to look at the Schrodinger wave equation. We're going to look at some electromagnetic radiation, the photoelectric effect, some Einstein equations, and just kind of generally review the historical development of the atomic theory that we talked about last year in year one chemistry. In the second video, we'll look more at the quantum numbers, the electron configurations, and just a little more depth than we did last year. So, like I said, this chapter is all about electronic structure. In order to get into the electrons, though, we're going to start by talking about some wave theory. So, wave theory involves just a few simple concepts. First, the wavelength, which we symbolize with the Greek letter lambda, is the distance between two corresponding waves from crest to crest or trough to trough. The top or the crest of the wave is also called a peak, so you might see that in the textbook. Now, frequency is something that's hard to understand just by looking at a picture because it involves the movement of the wave through space. So if we assume that all waves move at the speed of light, which is a safe assumption, and we draw two different waves here, then if both of these waves are moving to the right and we have some kind of detector set up here that's going to count the crests of waves, then let's say after 1 second, and remember the waves are moving at the speed of light, so they can go quite a ways in a second, we would count how many waves go by that detector, and that's the frequency. So frequency is oscillations per second. That's often measured in hertz, and we usually abbreviate frequency with this fancy F. Anyway, when we look at frequency, something that we usually correlate with frequency is the amount of energy in a wave. So, if the waves are all moving at the same speed, shorter wavelengths typically carry higher energies. Now, in your textbook, frequency is occasionally shown as V. I don't really like this a whole lot. V is actually saved for velocity in physics. So I'm going to use F for frequency just because that's a better, in my opinion, unit. But in your textbook, when you're doing your reading, you will see it as V. All right. Now, electromagnetic radiation is something that we talked about last year. Obviously, the portion of EMR we're most familiar with is the visible region of that spectrum, from violet down in the 400 nanometer range to red in the 750 nanometer range. Remember that light is just one form of electromagnetic radiation. Gamma rays all the way on the left, X-rays, ultraviolet rays, all have wavelengths that are too small to be detected by our eyes. And then to the right of red, we have infrared, microwaves, and radio waves, which are all too large. When you look at EMR, we can calculate wavelength and frequency using this equation right here, C equals lambda V, or in my opinion anyway, a better way to write that would be C equals lambda F. Either way, all right, they both say the same thing. Something that you're going to want to memorize, just a constant, is C. That's the speed of light. It's 3.00, accounting for sig figs, times 10 to the 8th meters per second. So light moves fairly quickly. That is the speed of light in a vacuum. That is not the speed of light through all mediums. Obviously, if you pass light through glass or through water and you see refraction, that's because the light is moving at a slower speed than it was before. So, all that stuff about waves, great, but there's one problem with that argument. Waves don't explain why objects glow when you heat them up. If classical wave theory was sufficient to explain that, then we actually wouldn't expect things to glow at all. Obviously, our observations of reality tell us that things do glow, so there must be some kind of failure in the wave description of how energy gets from point A to point B. So the guy who came up with this, who figured it out, or who started us on the right track, is Max Planck. So Max was studying what we call blackbody radiation, and that's the fact that as you heat up an object, it starts to glow. The problem is at a distance, right? If you graph out how much energy you absorb from light as it, is transmitted over time, that looks like a smooth graph. It kind of looks like that person there on the left walking up the ramp. So if we were to graph that, and we were to put time on the x-axis, and we were to put the amount of energy that's being absorbed on the y-axis, then at our macroscopic scale, over time, the amount of energy that's being absorbed would be pretty straight, right? Same wavelength of light, constant frequency, no changes to it. We're just absorbing energy. Waves predict this, but that doesn't explain why things start to glow, because when they're glowing, they're giving off a different amount of energy. So Planck theorized that if you were to zoom in on that graph enough, right, here's our time, here's our energy, that as each individual second goes by, right, the photons that are hitting the surface of that detector are actually imparting discrete amounts of energy to the surface. And so if you zoom in enough, that line is not actually smooth, it's staircased. Now, as you zoom out, right, the further away you get from a staircase, the more likely it is to look like a ramp. And that's kind of the same thing that we're seeing here. You can also kind of think about the energy associated with light waves like the population of a city. The population of a city can only go up by discrete integers. You can't go, welcome to Rockbridge, population 100.2 people. You either have 100 people or you have 101. When a photon strikes the surface of the detector, it either imparts 1 unit of energy or 2 units of energy or 6 units of energy. It doesn't impart 1.2 units of energy. It's going to be a discrete chunk every single time. Depending on the wavelength of that light, it's going to be the same chunk every single time. So like violet is always going to give us the same amount of energy. And we'll calculate that here in just a minute. Another thing that we want to think about as far as, this quanta is, once he established this, once he showed this to be a fact, it started to call into question some of, the observations we made about reality. And one of those things that had been a question for a long time was something called the photoelectric effect. Now, a lot of people think about Einstein, they think about the general theory of relativity, they think about special relativity. Einstein's Nobel Prize was actually for his description of the photoelectric effect, and he used information from Max Planck and one of, I forget the other guy's name, and his explanation of why the photoelectric effect occurs actually won him the Nobel Prize. But what is the photoelectric effect? So when you shine a light on a metal surface, if it's a fairly clean metal surface, and you set up a detector that detects electrons, you'll notice that as you shine light on that metal surface, it's just emitting electrons left and right. So the light is causing electrons to be emitted from the surface of the metal. Now, people couldn't explain that with classical physics, because if you think about a wave of energy, which is what we thought light was, just washing over the surface of the metal, there's no reason for that to kick off any kind of electrons. But if you think about light as having some particle-like behavior, those small quanta, then as the individual photon strikes the electron, that's what kicks it from the surface. Now, something else that they found was there were only specific frequencies at which the photoelectric effect is actually seen. Once you get above that frequency, you don't kick off any extra electrons, but the electrons themselves start whizzing by faster. They have more energy associated with them. So Einstein took this information, right, about the frequency and about kicking off electrons, and he took Max Planck's investigations into the quanta nature of energy, and he said, well, light must be comprised of these wave particle dualities that are able to strike the surface of the electrons and kick them out. Now, that's a pretty big jump, considering that everybody knew that light was a wave. It couldn't possibly be a particle, but as it turns out, he's right. The equation that he used to I guess prove that is that E equals HV, or again, E equals HF. Now, in the flame test lab that we did last year, you actually used a version of this. E does, let me write this a little cleaner. E equals HF, and F is, I believe it's lambda under C. So that would be E equals HC divided by lambda. So if you know the wavelength of light, say from the flame test, right? So remember last year that's the worst flame ever drawn in the history of online videos. There we go. We heated up like lithium. Lithium gives this nice red flame. The red flame is somewhere in the neighborhood of, we'll say 750 nanometers. 750 nanometers. We can convert that over to meters. I think it's 9 nanometers in a meter. That'll give us some number of meters, and then Planck's constant is in joules times seconds. C is in meters divided by seconds, and lambda would be in meters. So everything would cancel out except joules, and we'd be left with the energy of that specific photon. This helps us explain things like atomic emissions, all right? The fact that if you heat up a gas and then pass the light from that through a prism, it will give you a spectrum. You can see here this line spectrum for hydrogen, and this one for neon. So the electrons are giving off specific wavelengths of light, and they show up in the spectrum like this as solid bands. It's pretty interesting stuff. Now, the hydrogen spectrum is especially interesting because it's the simplest, right? The simplest atom, hydrogen. And so people usually start with any kind of chemistry law. They start with hydrogen. If they can explain hydrogen, then they can, move on to other more complicated atoms. So Johann Balmer in 1885 discovers a formula that relates these 4 lines on the hydrogen spectrum. So each one of these lines right here are related by this equation. 1 over lambda equals R sub H times 1 over n squared minus 1 over n squared 2, initial and final being those subscripts. So you don't need to know this equation. The Rydberg equation is famous, but you don't need to know it for the class. What we want to know is that this is what caused Niels Bohr to come up with the Bohr model of the atom. He was trying to explain why this relationship works. And in year 1 chemistry, Bohr gets a bad rap, right? He's sandwiched in the atomic theory unit between, what's his name? Ernest Rutherford's, discovery that the nucleus is mostly empty space, and that, Rutherford's atom had a nucleus and then it had electrons going, right around it, and they were all equidistant from the nucleus. And that was, Rutherford's model. And then we go down to Bohr and we go, well, Bohr said there's the nucleus, all the protons and neutrons, and then there are these electrons in orbits outside of it, different distances from the nucleus. And in year 1 chemistry, pretty much all we say is, and he was wrong, and we move on to Louis de Broglie. And, we don't really talk about the fact that Niels Bohr's model was actually a really good model. In AP, though, we're going to talk about that. So Niels Bohr takes Planck's assumptions, and he uses his model to explain them. So first, he says electrons in an atom can only occupy certain orbits. They have to be a certain distance away from the nucleus, corresponding to a certain amount of energy that they have. Now, think about, we'll get to that in a minute. The second thing he says is that electrons are allowed to have certain energies. They're not going to give those energies off. So at the ground state, right, an unexcited electron, it's just going to, ride around the orbit. It's not going to give off any light. We're not going to see anything being, radiated out of the atom. The third thing he says is that energy is only absorbed or emitted in such a way as to move the electron from one allowed state to another. So if, the first energy level is the first allowed state, we'll call this the ground state. Then on our energy graph here, right, so the y-axis is energy, exactly at this point would be like number 2, right here would be number 3, and these are allowed states. You can't just like drop an electron right there on that X. That's not allowed. So he's saying in order to get this electron to move from the ground state up, it has to absorb enough energy to go exactly up to level 2 or exactly up to level 3. You can calculate that with that same formula we just used, equals HV, or remember when you see V, that's F. I believe that V is actually nu in Greek, equals, no, that's not right, never mind, I take that back. Nu I think is frequency, so that could be H nu, but just use the F. The F is better. Now, if you look at some of his more advanced mathematics, because he was very good at math, he took that Rydberg equation, or the Rydberg constant, and he used it to calculate the change in energy that occurs when an electron moves from a ground state to an excited state. Now, it worked, and it does describe the energy that is given off when an electron moves from, say, the first energy level to the second energy level for hydrogen. But here's the problem. It only works for hydrogen. And in classical physics, if you have a negative particle like an electron going around and around and around and around and around a positive nucleus, well, the force of attraction between positive and negative charge is going to make that negative electron fall into the nucleus and annihilate itself, basically. On its way down, it's going to actually form a spiral. So you're going to get this positive charge, and the negative charge is going to start out here. And as it circles, it's going to spiral into the nucleus. And an electron that spirals towards the positive actually should give off radio waves. And we know that, according to classical physics anyway, and we know that atoms don't just sit around giving off radio waves. So that's why Bohr's model is not an accurate representation of reality. Now, the issue is he assumed, as did everybody, that this orbit around the atom was circular in nature, and that's not the case. So the wave model, all right, the important things, though, that come from him say that electrons are only able to exist in discrete energy levels. Now, this is true. I mean, you don't find electrons everywhere. You only find them in certain places. He also figured out that in order to get an electron from level 1 to level 2, from point A to point B, there has to be some kind of energy transfer. Now, just not to run off on a wild tangent, but this energy transfer is actually useful to us in day-to-day life if you've ever seen a neon sign or if you ever wanted to make a laser. So, like, if you want to make a laser, you have your ground state electron sitting here. You have your first energy level or second energy level, whatever it is. If you constantly put energy into this electron that makes it jump up and immediately drop back down, it gives off a photon. It gives off a wavelength of light. Well, if you do that fast enough, you basically get a constant stream of photons, and that's how you end up with a laser, which is, useful. Lasers are cool, and, we use them to cut steel, and that's awesome. Another thing that's useful for is a neon sign. If you put an atom between a cathode and an anode, so here's my battery, right, positive side, there we go, and I start to fire electrons, right, so each one of those dots is an electron, at the atom, well, it's going to absorb some of them and get excited, and it's going to give off photons as those electrons go by. If you put a bunch of atoms into a tube, put a cathode and anode in both ends, and run electricity through it, well, that's how you get neon signs. You get the neon to light up. It's absorbing energy. The electrons are jumping from the ground state up to the excited state, and, they jump up, they drop back down, they give off a wavelength of light. The reason they give off the wavelength of light is the law of conservation of energy. Energy has to be conserved. So however much energy I put into the ground state electron, when it drops back down from the excited state, it gives that same amount of energy off in order to conserve the energy. So that's how we get our visible light from a neon sign. Now, if we move from Bohr into the more modern version of the atom, we have to talk about Louis de Broglie. And Lou de Broglie theorizes that if light can have material properties, that is, if light can act like a particle, then maybe particles can act like waves. And he says that, lambda equals h divided by mv. Now, mv, this is important, mv is momentum. Momentum. When you take physics, you might see this as p, momentum. There we go. So another way this is often written is h over p. Lambda equals h over p. This is chemistry, though, so we'll just keep with the mv, but we do want to know that that's momentum. He said that, if light can behave like a particle, then maybe particles can behave like waves. Now, this is the de Broglie wavelength formula. It's not the same thing exactly as this formula from a minute ago, which was HV. So this is the photon energy wavelength formula. This is how you calculate the energy of a singular photon, which I just broke my own rule. It should be HF. Okay. This equation over here, de Broglie's equation, is the formula that describes the wavelength of a massive particle. Now, something to think about. All particles have a wavelength, but wavelength is inversely proportionate to the mass. So because we are so big, our wavelength is so small, it's basically negligible. But if you take a particle like an electron, which has a mass that is super, super, super tiny, right? It's like 1/1800th of a proton's mass, right? It's tiny. Then its wavelength is going to be substantial, it's going to be measurable, it's going to be significant. Now, sorry, got to hit myself there. Two different screens. There we go. So as they looked at that, right, as they looked at this wave particle dual kind of description of reality, there became some issues. All right. First of all, a lot of people did not accept it. That was the first issue. Even Einstein was not a big fan of it, and we'll talk about why in just a second. But as people started to work the math out around it, they started to find that it was an accurate description. So Heisenberg showed us that the momentum, mv, and the position of the electron were related, but there was a problem. This is the momentum, right? mv, momentum, there we go. And this delta x is position. Remember, delta means change in, right? So this is an inequality, not an equality statement. Still have Planck's constant here. Wow. Come on, pen. There we go. Planck's constant. All right. So we learned about the uncertainty principle in year one chemistry. We said, hey, you can't know the location and the speed of an electron at any given time, and that's where we stop. So now let's take it a step further. Let's actually look at the equation. So since it is an inequality, as this number goes down, in order to keep the inequality the same, this number must go up. So what this is saying is, the more accurate I know that the position, right, the smaller the change in position is. So as the change in position gets smaller, I'm pinpointing where that electron is in space. The greater the change in the momentum must be in order to account for that decrease in delta x, right? Because at all costs, the inequality must remain true. If you switch it and you say, okay, well, I want to know the momentum of the particle, well, as delta mv gets smaller, well, delta x has to increase. So that's what we mean when we say you can't know the momentum and the position at the same time with the same level of accuracy. As you know, with increasing accuracy, one value, the other value compensates, right, in order to keep the equation true. This leads us to Schrodinger, right? So Schrodinger is probably one of my favorite parts of AP Chem. So this thing right here, that's Schrodinger's wave equation. Looks fancy. A couple things you're going to see in here. First, there's some partial derivatives. These are partial derivatives right here. You don't obviously need to know how to do calculus to take AP Chem, but that's a partial derivative. We have an actual derivative over here. We have Planck's constant there and there. Nice to look at, all that cool thing. Here's the big takeaway. This thing right here is psi. Psi is the most important part of this equation. You want to be able to recognize psi. PSI, it's a Greek letter. PSI, that's psi. Now, when we talk about Schrodinger's wave equation, we could spend hours talking about this because it's a really interesting concept. First, no one really knows what psi is. So psi is the wave function. That's what psi is. So we can write that down. I'm not going to say we don't know what the variable is. So this is psi. It is the wave function. We know how to, we know what the wave function tells us, but actually what it's describing is something that we're still wrestling with. There's still competing views on this. But we'll talk about that in a second. First, let's talk about quantum mechanics. So the wave function is really important to quantum mechanics because at its heart, quantum mechanics tries to describe reality in terms of wave behavior. So the ideas that underpin quantum mechanics really depend on you understanding that all matter has both wave-particle duality. If it didn't, you could not describe reality in terms of waves. Now, just something that's kind of interesting, if we keep looking at Schrodinger's equation, the square of psi gives us the electron density. Now, there is something interesting here historically. Schrodinger, well, actually, let me get here we go. I'm going to go back. So let's draw a graph. So if you run Schrodinger's equations, all right, you actually can graph out the answers. And you're going to get some kind of wave, all right, just like that. Now, Schrodinger's idea was that this was a graph of electron charge density. So he kind of imagined the electron as a wave that's kind of like smeared out in space. That's what he thought. He was actually wrong. All right, that's not how we have to think about the electron. It took a different guy. His name was Max Born, right? Max Born, who said, that's not how we want to look at this equation. So let me redraw this graph. So we've solved the equation. And when you solve, let me write out this equation here. It's H over 2M. And then we have partial derivative psi over d squared plus psi. The derivative of psi over time. Okay, so when you solve this big thing, this equation, the answer that you get is psi. And psi is a function of x. So we graph it on the x-axis, and we get some kind of wave. Okay. Now, what Max Born says, Max Born, this is one name here, he says, well, actually what you should do when you get this number is you should square it. He said square it. And this is going to give you the probability density of finding an electron at a certain position. All right, what do I mean by that? Well, let me switch colors. Let's go over here and let's grab blue. So anywhere where the graph touches the x-axis, that's something that we call a node. So here, y is equal to 0, right? So the y-axis has our psi value. So anywhere where y equals 0, we have a 0% probability of finding an electron, all right? So we call this a node, all right? And the nodes are going to come up in the second video when I talk about the actual shapes of the orbitals. The nodes are regions where you don't find electrons. On the other hand, places where you have a peak, and the peak can be positive or negative, right? These are places where you are likely to find an electron. So right here, I have a good chance. Right there, I have a good chance. I have a good chance right there. I have a good chance right there, right? Anywhere there's a peak, I might find an electron. This position that I'm circling is going to be the highest probability. Highest probability. So this is where this equation starts to mess with the view of reality. It's something that Albert Einstein didn't like. So if you've heard the quote from Albert Einstein that God doesn't play at dice, he was actually referencing this kind of outcome. So at its base sense, the Schrodinger wave equation is probabilistic. There we go, probabilistic. It's not deterministic. It's only determined when you make a measurement. When you make a measurement, and like, let's say I find the electron, there it is, boom. Well, now everything else goes to 0. It can't be in two places at once. So it's only deterministic when you measure it. Otherwise, it's just probabilistic in nature. So, you know, a lot of people didn't like that about the Schrodinger wave equation, but as far as I know, that's the way that reality is. That's one of the great things about math. It doesn't care about what you like. Now, the next kind of interesting thing about this graph is, even though I have these nodes, I'll just draw a simpler one there. Just because I have a node right here and that X is the most likely position, that doesn't mean I can't find one right here or right there, right? Because another problem with psi, right, is we don't really know what psi really kind of is. Is it just what one electron is doing? Or is it a series of electrons? Like, is it the aggregate of all the electrons being tested? The truth is out there, right? We don't actually know the answer to that question. So this could be because it's a waste of time. Like, really, it could be one of those things that we just can't answer. It could also be one of those things that whomever does answer it will become one of those people that AP chemistry teachers talks about, like, Max Planck or Louis de Broglie. So if you're interested in that kind of physics stuff where it bleeds over into chemistry, go knock yourself out and make sure you put my name in the footnotes. All right, so in the next video, we're going to look at the quantum numbers and we're going to look at the electron configurations and the orbitals a little closer. Big takeaways from here. The structure of the atom, as far as quantum mechanics is concerned, is a probabilistic structure. So when we look at this graph, which I know we saw last year, this is an s orbital. It's not really a closed sphere. It's not an eggshell. It is a probability density map. The more dots, the darker the color, the greater the probability of finding a electron in that, or an electron in that area. As you get further, in this case, from the nucleus, those dots diminish, and so you have less of a probability. So that's what we want to take from the Schrodinger equation. All right, if you have questions, be sure to send me an email.